Hi Year 11. I'm just going to go through the atomic physics test with you. I'm going to do it in two videos, one for the multiple choice and one for the written answers. Now, just a quick point, when you fill in your grid for your multiple choice, hopefully you can see what I've done is I've coloured in the little rectangle that shows underneath the letter. You need to be doing that, and I want you to get into the habit of doing that, because in your real exam you will get a grid that looks exactly like this, and a computer marks it and they look for that mark, and so if you circle it, it won't be able to read it and you won't get any marks for your whole exam. So please, in future, just get into the habit of doing that for me, and if you did that, thank you very much. Okay, let's have a little look at the multiple choice then. So question 1 is about a nucleus and the number of neutrons it contains. Now, it tells me that the nucleus emits an alpha particle, and what I've said is that is a helium nucleus, which has 4 nucleons, 2 protons and 2 neutrons. Okay, and it says how many neutrons are in the nucleus after it has emitted this alpha particle. So we know that the alpha particle has 2 of the neutrons, so the difference between the original number and the final number has to be the 2 that get kicked out. So it'll be 136, because the difference between 138 and 136 is 2. So that's question 1. Question 2, excuse me while I move the camera. I better make that more obvious for you. Sorry, it's not showing up very well. Okay, so we can see it says the graph shows the decay curve for one particular radioactive nuclide, and it gives you the count rate. Hopefully you can see that to begin with it is 2,200. Wait for it to go back and focus. So that means that because it's a question that is asking about the half-life, you can see there, I need to think about what the half-life will be. Now, to find that, I know that the count rate will have to half, so I'm going to look for when my count rate goes to 1,100, because that's half of the count rate has decayed. And then basically all I do is I track across at that point, and I can see that occurs at 2 days. So the count rate has halved from 2,200 to 1,100 in 2 days, because 2,200 was at 0. 2 days later, that's the value that I get, so that gives me C there. Okay, so question 3. Sorry, I've not left much room for working here. So, a radioactive substance has a half-life of 2 weeks. At the beginning of an investigation, the substance emits 3,000 beta particles per minute, and then it asks how many will it be emitting per minute after 6 weeks. So, the half-life is 2 weeks, so in 6 weeks I will have had 3 half-lives. Okay, so if I know I originally had 3,000, I'm going to half that number 3 times for 3 half-lives. 3,000 goes to 1,500, 1,500 goes to 750, 750 goes to 375, which gives me B. The last question on this page, sorry, is question 4. Hopefully you can see that there. A radioactive element has a half-life of 70 seconds. Just a quick note, circling things like this, quite helpful so you don't miss numbers. The number of emissions per second, N, of a sample of the element is measured at a certain time, and it asks what the number of emissions was per second 70 seconds earlier. Well, if the half-life is 70 seconds, then 70 seconds earlier was 1 half-life prior. So 1 half-life earlier would have double the amount of emissions. Okay, and it tells us that the number of emissions at this point now is N, so 70 seconds earlier would be 2 lots of that. Gives me 2N. Hopefully that's okay for you there. Okay, question 5. Let me move this back up, sorry. Okay. Here's S, is the radioactive source. It's emitting alpha, beta and gamma. So that will be doing that in all directions, right? So there'll be alpha coming out, there'll be beta coming out, there'll be gamma coming out, and they'll all be coming out in all directions, to be clear. Okay, so we've got the source is emitting radioactivity. Now we know that we've placed the detector here, and that's 5 centimetres away from the source, and we also know that in between the detector and the source is a thin sheet of paper, and it asks you about which type of radiation can be detected. Well, a thin sheet of paper will absorb alpha, so any alpha that's travelling through this way will get stopped by the detector, and it will be absorbed by the paper, sorry, and it will be absorbed, so it will not reach the detector. But beta and gamma are not stopped by paper or air. That's only alpha. Okay, for beta I need some aluminium, and for gamma I need meters of concrete or lead, which I don't have. So beta and gamma will get through. Okay, so on this side I will have beta and gamma only, which gives me C. That's a memory game to remember what stops each type of radioactive emission. Let's see if I can make that a bit clearer. Sorry. Okay. In the atomic model, we've got a central mass. Hopefully, we know that we refer to that as the nucleus. Okay, that's where we find the protons and the neutrons, and the particles that orbit the nucleus are the electrons. Okay, I can't help any more than that. You just absolutely need to know the name of the different parts of the atom, and that means that the central mass is the nucleus and the orbiting particles are the electrons, which gives you D. Okay, last one on this page. So we've got 400 milligrams of radioactive material, and it's emitting alpha, so remember that's a helium nucleus. The half-life of the material is 5 days. Okay. Now we are looking for the mass of the material that remains after 10 days. So that is 2 half-lives later. So if I start with 400 after 1 half-life, that will halve to 200. And after the second half-life, that will decay to 100, which gives me C. Okay, next question is question 8. Let me move the thing again, sorry. Alright, a radioactive nucleus emits a beta particle, otherwise known as an electron. What happens to the proton number, the atomic number of the nucleus? Now, what we have to think about is how beta particles are emitted, and back to our decay equations. For beta particles to be emitted, what has to have happened is a neutron in a nucleus turns into a proton and an electron, and that's to conserve charge. Okay, so a neutron is neutral, it has 0 charge. A proton has a relative charge of +1, and an electron -1. 1 minus 1 is 0, charge is conserved. Okay, so a neutron inside here converts to a proton and an electron, but the electron doesn't want to stay in the nucleus, so that bit gets kicked out and the proton gets left behind. What happens to the proton number? Well, now I've got one more than I had before, so it increases by 1. Okay, last two, number 9 and number 10. When measuring the emissions from a radioactive rock brought into a lab, a teacher mentions that background radiation must be taken into account. Again, this is just one that you absolutely have to know. There could be lots of reasons for background radiation to be there, but what it means is that there is radiation in the lab even without the radioactive rock being there. Okay, so you could turn on the detector and it would be reading some radiation even when you haven't brought that rock there. Okay, so that's just D, that's just knowing the definition of what background radiation is. And last but not least, question 10. which diagram could represent the structure of a neutral atom. Neutral is to do with the charge, so I need the total charge to be 0. Okay, so I've got, let's start at the beginning, would be helpful, wouldn't it? We've got +1 in the nucleus from 1 proton, and -2 from the 2 electrons orbiting. So the total charge of this one, oh, let me move the screen down, sorry, is -1, so it can't be A. Okay, I've got +1, +1, -1, -1, and a 0. I should put the zeros in as well. The total charge here is 0. -1, +1, +1, 0. That gives me a +1. -1, -1, 1, 1, 1, 0, 0, 0. So I've got 3 minus 2 gives me +1. The only neutral atom is B. Okay, hope that has helped. I'll move on to the next video with the structured written answers for you next.